Again, good afternoon, grade 8. We are now done with
Afternoon, sir.
introductory activity. So let's move now to the lesson proper. Okay, let me share my screen. Give me a minute. Okay, the atomic structure. Can you see my shared screen now?
Yes, sir.
John Dalton's atomic theory. Okay, let's start with Dalton's theory. The idea of an atom began to be operational significance when John Dalton was between 1766 to 1844, an English scientist, showed that this could explain the existing laws of chemical combinations. Remember that your chemical combinations also has properties, right? And has also some results or outputs. He chose the word atom to express the idea of invisibility because during that time they cannot actually explain the invisible particles. That is why it was coined atom by John Dalton. He pictured an atom as a tiny indestructible sphere with mass. Okay, Dalton, because of his contribution to atomic theory of matter, is known as one of the fathers of modern physical science. The postulates of Dalton's theory. Okay, the modern atomic theory defines an atom as the smallest particle of an element which can enter into a chemical combination. The idea is embodied in Dalton's atomic theory. The basic postulates, if which are as follows. Please take note of the postulates. Number one, matter is made up of extremely small indestructible particles called atoms. So in John Dalton's theory, atom was described as indestructible, meaning to say it cannot be destroyed. Okay. Number two, all atoms of a given element are alike. Okay. All atoms at a given element are alike. So like for example, atoms of hydrogen are the same all throughout. All the hydrogens are the same. All the oxygen are the same. That's in the postulates of John Dalton. Number three, atoms enter into combination with other atoms to form compounds, but remain unchanged during ordinary chemical reaction. So just like um, when we mix sodium and chlorine, okay, we can form sodium chloride. So according to John Dalton, it remain unchanged. That is an ordinary chemical reaction because we don't actually extract water in it. Okay. Number four, atoms can combine in simple numerical ratios such as 1 is to 1 or carbon monoxide, for example. So one atom of carbon and one atom of oxygen, carbon monoxide. How about um, 1 is to 2, CO2, for example, carbon dioxide. So one atom of carbon is to two atoms of oxygen, and so on. So that is the chemical numerical ratios of combinations. Dalton's atomic theory gives a sufficient explanation to the three laws of chemical combination, which are number one, the law of conservation of mass. Again, the law of conservation of mass. That's number one. It states that when an ordinary chemical reaction occurs, there is no detectable change in the masses of the substances involved before and after reaction. So this means that the reactant is equal to the product. Okay, whatever the reactant, it should be seen in the product. This is one way also to balance your equation in chemical balancing. Okay? Whatever you see in the reactant, you can actually see also in the product. According to the third postulate of Dalton's theory, when atoms combine with other atoms to form compounds, they remain unchanged. Since the same atom are present before and after chemical reaction, the total mass of reactants and products must be the same. Okay, again, since the same atoms are present before and after a chemical reaction, the total mass of reactants and products must be the same, just like when you balance equation. Are you still with me? EM, Janine and Rabi?
Yes, sir.
How about EM?
Sure.
Okay. The second law, or the second law that the postulate of John Dalton explained is the law of definite composition or the law of definite proportion. It states that the given compound always contains the same element in the same percentages by mass. When two elements combine to form a given compound, they always do in a fixed proportion. Okay? Proportional. Okay, um just like when you mix again sodium and chlorine, okay, it should be the same proportion. That is according to the law of definite composition or the law of definite proportion. Let's tackle more about this later. Dalton explained the law of definite proportion by considering the second and the third postulates. If all atoms of elements are alike and atoms combine in a fixed numerical ratios, then the percentage composition of a compound is always the same regardless of its origin or method. Percentage compound composition, this means to say that the number of um the number of, for example, sodium and the number of chlorine, once they perform, or shall we say have the chemical reaction, their composition is the same or equal. Okay. The third law is the law of multiple proportions. It states when two elements combine to form more than one compound, the masses of one element which combined with the fixed mass of the other elements are in a ratio of small whole numbers such as 2 is to 1, 1 is to 2, 2 is to 3, and etc. Okay, just like what I'm telling you a while ago, carbon monoxide, carbon dioxide, water, the H2O, what else? Potassium permanganate. So those are in small ratios. Dalton's idea of undoing the atom of an element with a characteristic mass offered an explanation for the laws of chemical combination. By the way, those are the laws of chemical combination. The mass became known as the atomic weight. Okay? Do you have now your periodic table of elements?
Yes, sir.
Today, the unit in which atomic mass are measured is defined by the international agreement. Okay? We have actually an agreement internationally to have a uniform idea about the measurement or the atomic mass. The unit is called the atomic mass unit, AMU. Okay? The symbol is AMU. Carbon has atomic mass of 12. This means that one carbon is exactly 12 AMU. The atomic weight of an element is now defined as average mass of its atoms relative to the mass of an atom arbitrarily assigned as 12 AMU. Again, it's 12 AMU. If you're going to look at carbon, let me share my screen for carbon. I'll let you see. Open my periodic table. explain to you the atomic mass and the atomic number. By the way, the one that I actually given to you, the periodic table is complete, and those are the latest update for the periodic table. Let me share my screen. Okay, can you see my shared screen now? Can you see my shared screen? Grade 8.
Yes, sir. Yes, sir.
If you're going to look at carbon, the atomic number for carbon is 6, right? Okay. The atomic mass for carbon is 12.01. Sure. Why it's 12.01? It is not exact number. Okay? Because there are a lot of carbons, although they are the same. Like for example, um, carbon which has an atomic mass of 12 alone, or 12.5. So those are called isotopes. So there are a lot of isotopes in a particular element. Akong balikon. They are not exact. They are not actually in a whole number because there are a lot of element or versions inside that particular element. Okay? Like for example, ferrous, iron. Di ba natay iron or ferrous sulfate, ferrous oxide, ferric chloride. Okay? What else? Um, Potassium. There are a lot of potassium also. What else? Iodine. Okay, there are a lot of iodine also. So it depends upon the version of an element. So let's coin that one as version in order for you to understand it easily. It is not whole number again because it means to say that it has a lot of versions or a lot of isotopes. Isotopes, these are elements which has the same atomic number but has different atomic mass. Then lain sila og atomic mass pero parehas sila og atomic number. Okay? Let's continue with the discussion. Electrical nature of an atom. Quite a number of experiments demonstrated that two kinds of electrical charges are possible. Okay? Bodies bearing the same charge repel one another just like your magnets, while bodies of opposite charges attract one another. Okay? This is known as the Coulomb's law. The law was formulated by Charles Coulomb. This is between 1736 to 1806, a French physicist. The Coulomb, which is now with the symbol C, is an electrical unit of charge, was named in his honor. Other electrical discoveries were made years later by Luigi Galvani, that's in around 1737 to 1798, an Italian scientist, was successful in passing a current by making use of energy derived from a chemical charge. He pioneered the study and use of electricity. So he actually have this experiment about the alternating current and the direct current. Alternating meaning AC, your corriente, the regular current, and the DC or direct current, which is your battery. The invention of battery by Count Alessandro Volta, that's around 1945 to 1827. He is actually an Italian physicist, sparkled widespread investigation into the phenomenon of electrolysis or electrolysis, the separation of electricity. It was followed by Sir Humphrey Davy, that's around 1778 to 1829, and Michael Faraday, that's around 1791 to 1867, who studied the electrical decomposition of numerous compounds. Faraday proposed the quantitative law known as the Faraday's law to express the magnitudes of electrolytic effects. He suggested the existence of fundamental unit of electricity to account for his results involving in the electrolysis or the separation of electricity of solutions of aqueous acids and salts. This idea extended George Stanley, which is around 1826 to 1911, an Irish physicist who proposed the name electrine for the unit charge. This experiment and other similar ones performed during the time of Dalton's strongly suggested that a fundamental relationship existed between electricity and the structure of matter. Sure, why do we need to tackle the discovery of electricity? Because it is actually connected to the atomic theory, the structure of matter. Remember that your atom or your element or atom in the element is actually moving because of this electricity. However, Dalton's atomic theory did not give an explanation to this phenomenon. That is why they further studied, okay, the electron. William Crookes, 1832 to 1919, an English chemist, using a vacuum discharge tube called Crookes tubes, showed that there was some kind of matter coming from the cathode. This is the negative electrode. The particles are called cathode ray. Okay. Now, the Crookes tubes are called cathode ray tube. Okay. CRT. Are you familiar with CRT? Because they originated from a cathode. Are you familiar with CRT?
No, teacher.
Who among you here have observed before bigger monitors or has bigger monitors at home before? Or bigger TVs? Bigger TVs. Itong dagko ba? Karaan yung TV. Okay. Okay, Janine has before. Those are CRT TVs. Okay. Cathode ray tube. Okay. LCD is different because liquefied crystal display. Cathode ray tube uses what? Negative electrode to project an image. Okay? Again, you can observe this one in old televisions. Katong dagko kayo nga televisions. Okay, nasa gitawag og picture tube. That is actually the CRT, the cathode ray tube. Right? Just like this one. Okay, this is actually a cathode ray tube. Okay, they uses electron. Okay, the negative electron to project an image to the cathode ray tube. Numerous experiments made by Julius Plucker and Johann Hittorf and William Crookes and others showed that the cathode ray exhibit the following properties. Number one, cathode rays are emitted from the cathode when an electric current is passed through an evacuated tube or your cathode ray tube. The rays travel in a straight line. If small objects are placed in the discharge tube, The rays form a shadow. Number 3. Cathode rays, upon striking a glass or other material, will cause it to fluorescence or fluorescence, muhayag, musiga. Cathode rays bear a negative charge. This is shown by the fact that they are attracted towards positively charged objects held outside. Sir J. Thomson or Joseph John Thomson in 1856 to 1940, an English physicist, after the series of investigation, established the particle nature of cathode ray. He actually studied the cathode rays, how these cathode rays work, and how these particles also um, react to certain materials. He further concluded that the cathode rays are negatively charged fundamental particles found in all atoms. Cathode rays are now called electrons. Okay? Your cathode rays now is called electrons. J. Thomson helped revolutionize the knowledge of atomic by his discovery of the electron. How? Later on, we will discuss J. Thomson's model. Eugene Goldstein, a German physicist known for his work with electrical phenomena in gases, discovered a new particle which is called canal rays or canal rays. The name arises from the fact that the rays are attracted the cathode and pass through the holes called canals in the cathode. These particles are positively charged. Why? Because remember that your cathode ray is negatively charged, it is attracted to, or the positively charged is attracted to negative. Therefore, it will pass through the small holes, and they name it canals. Goldstein hypothesized that these particles could be what were left out of the atom or molecules after electrons have been pulled out. Canal rays are now called as or known as protons. Again, canal rays are now called or known as protons. The discovery of electrons by J. Thomson and X-rays by Wilhelm Röntgen, a German physicist, which resulted from the research of cathode rays, violated Dalton's postulate that atoms are indestructible. Remember what um, J- what Dalton's postulate are telling us, that number one, atoms are indestructible. So it actually violated Dalton's postulate. At this point, an atom could be broken down into two parts, namely a tiny negatively charged electron and a massive positively charged ion. Thomson's or J. Thomson's atomic model. Mm-hmm. Let me check. Okay, let's continue the discussion with J. Thomson's um, model by next meeting. Okay, please study in advance the lesson. We are now in J. Thomson's atomic model in order for you to interact in the class, or you can share your research in the class with that particular topic. All right? Am I making that clear, grade 8?
Yes, teacher.
Okay, I think that will be all for today, grade 8. Thank you for your time. Thank you for your participation, Rafi, Janine, and EM. Have a nice day, everyone. Goodbye.
Bye, sir.